Meanwhile, it's my pleasure to introduce Jose Cano. Please.
Okay, thank you, Paul, for the introduction. It's my pleasure to be here today. So the quality of the talks have been great today. I hope to keep at least similar level. So let me tell you what we have done lately in my group at Glasgow. So I'm going to talk a little bit about how to accelerate AI at the edge. So first of all, I want to introduce some of my team, not everybody's here. So the first thing I want to introduce is that today some people say about this differentiation between machine learning systems. So I created my group, the Glasgow Intelligent Computing Lab, in 2018. So the reason for that was I have been a hardware architect and compiler engineer over the last years, but I realized that we were working on deep learning, and actually, so the machine learning people were not talking much to the systems people. So we said, okay, let's create a group to put together to work at the intersection of computing systems and machine learning. And this is what we are doing in our group. So our group is part of the system section in the School of Computing Science, and right now we have collaborations with several companies and research groups across the world. So the first question I want to put on the table, and maybe you all know about that, but why AI at the edge, right? So there are several reasons that maybe most of you know, but it's worth to just remind them. So latency, real-time constraints. So some applications cannot go to the cloud. So just imagine a driverless car trying to detect if it's stop or not, sending the computation to the cloud. It's not going to work, right? So you can kill someone. So bandwidth, even with 5G, there is a lot of information we need to send to the cloud, and sometimes even these technologies is not enough because the amount of data is huge. Reliability, sometimes there is no connection. Imagine a rescue team in an isolated area, there is no connection, you cannot rely on the cloud, right? Security and privacy are emerging concerns, and of course, especially for banking or medical applications, we want to keep our information local and secure and private. And power consumption and cost is an increasing concern, and we're going to have cost-efficient and cheap solutions. So the problems is that we have bigger and bigger and bigger models, right? And we have constraints, very limited devices. And how do we do that, right? So how can we map these demanding applications on these constrained devices? So the first concept I want to introduce is the concept of deep learning acceleration stack. So we have been developing this concept over the last 2 years and was finally accepted at TACO recently. So at the top of this stack, we have full precision neural network models and datasets for different types of data, image, video, voice, text, and so on, everything, all the models that we have today. And at the bottom, we have the hardware, right? So we have different types of devices, and particularly in our group, as I mentioned before, we are focused on edge devices, right? So the idea is that in between, we have other layers that actually, the choices that you make on them are going to affect how your model runs on the hardware, right? So the first one that we can consider is optimization techniques, and here we have a bunch of them: pruning, compensation, neural architecture, hyperparameter optimization, distillation, and so on and so forth. Below that, we have algorithmic primitives and data formats, different ways of, doing an algorithm for a convolution, gen, binograph, compression format, when we need to deal with the sparse information, even encryption formats and protocols. So we need to consider all this. And below that, we have a huge layer of system software. Here we have libraries, programming models, frameworks, compilers, and so on. So as I said, what happens, right? So you can select an optimization technique, for example, sparsity. 2 years ago, we selected, we have a sparse model, and we realized that the model was running slower than not considering the sparsity. We were not dealing, efficiently with the sparsity, right? So the idea is that the choices that you make, you need to select them across the stack, and actually, providing at the end hardware software to design, which is the purpose of my talk today. Right. So let me tell you what is going to be the outline of the presentation. I will introduce the methodology that we are using for developing this accelerator, Sept, and then I will give you 3 examples of recent work that we have done using our methodology. So first of all, let's start describing how or why to develop specialized accelerators for AI. Well, I think a lot has been said these days about that, but the main thing is that, as we know, specialized accelerators can make AI faster and more energy efficient. This is a very important point, especially on edge devices. It is also true that edge devices are more and more incorporating FPGAs, and as we have discussed a lot today about FPGAs are circuits that we can reconfigure to our needs. The problem is that the current solutions that we found for developing AI accelerators on edge devices have high development costs, and today some people have been also discussing about that. Anybody can imagine what is the main bottleneck here to develop accelerators? Any guess? Programming. Okay. True. Yes. Well, and because of that, we have HLS, right? So in order to not program very low, right? Or VSDL, what we have is high-level synthesis. The high-level synthesis is very slow, right? If you want to iterate and propose a design and you want to iterate over and over, right? If you want to synthesize the design every time, this is super slow. In the board that we are using, that I will show you later, every synthesis takes 1 hour, right? So typically we can have 15, 20 iterations to get a design that actually meets our needs, right? So this is very slow. So for those that don't know high-level synthesis, so let me give you just the quick idea. Essentially, instead of programming in low-level, very low, or VSDL, what we do is to use a high-level language to make easier the description of a city. Okay. So for example, in our case, we are using System-C, but you can use also MATLAB or C, C++, any other languages. So basically what we do, we write this program, and with a set of libraries, the HLS compiler that was also described today, we generate the RTL design in Verilog, for example, and then we do the synthesis that, as we also, people discussed this morning, the place and routine is slow and needs to be good. But the idea is that here, doing these iterations to develop the accelerator is also very slow. In addition to that, something that we found, okay, I have this board and I have these models, but I want to use TensorFlow or I want to use PyTorch Micro. How do I pull together these two things? It's not easy, right? How to link the development with a specific framework is also a barrier. So we realized about these two things, and in order to solve that, what we propose is a design methodology called SECT to efficiently do the development of FPGAs-based accelerators. So basically, what we do instead of doing synthesis all the time, we combine quick or fast simulation with a few iterations of synthesis on the real hardware. Clear idea, more or less? Fine. So let me tell you a little more about this methodology called SECT, System-C enabled co-design of beginner accelerators. So we published this paper 3 years ago, the swap path, and essentially what we have is two loops. As you can see here at the top, we have this dotted loop, right? Basically, we have an application framework, whatever it is, an acceleration driver that interfaces the framework or the program with the accelerator, and we have here our accelerator, and that's fine. If we only rely on that, as I mentioned, we need to run all the time in real hardware. So what we do is to have this alternative loop here in green. Basically, we iterate and develop, right, and tune the accelerator only simulation, and eventually we do the synthesis to measure real performance, real memory transfer times, and so on. And just to make sure that what we are designing in simulation actually match real performance and hardware, right? And that's the idea, right? Combining these two loops, I would say. So let me give you a bit more information. Let's dig a little bit more into the SECT itself. So the framework, is able to run DNN models, and also run, of course, the models in CPU, full models, right? End-to-end execution. Examples of frameworks, well, anything that you can imagine. TFLite, TensorFlow, PyTorch Mobile, Picker, Llama CPP recently reduced, and so on. So the driver, as you can imagine, is an essential component because actually manages the communication and the interaction with the accelerator itself. So here is where we are actually doing part of hardware software co-design, right? So we co-design the hardware, so the data packing, the DMA transfer that we do with the hardware, right? On this component, right? So it's important to make sure or be aware of what the real hardware is offering. How many processing elements? How big are the buffers, right? So there's the VSR memory. So another component is the System-C accelerator. Here, what we do is end-to-end simulation to the NN models based on transaction level modeling. And this is, as I mentioned before, is the starting point for the high-level synthesis, right? We also have System-C test bench. Obviously, when we are designing an accelerator, we want, for example, to test some isolated processing element, not the full thing, or we can test isolated elements and also do random or sample data simulation. The synthesis, I already talked about that, and well, also the real hardware is here, right? So the real execution, the execution real hardware I also mentioned before. So essentially, the design loop, as I mentioned, is based on combining these two types of execution. How many of them? Well, it's all about profiling. So what we implemented in this framework is a lot of profiling tools, right? So to get information of what is happening, right, in the execution. For example, in simulation, we can get cycles, estimation of memory usage, and this thing. But eventually, as I said, we need to map onto the hardware and see, okay, how are we matching the cycles? What is the memory transfer time, right? We need to check that. So at the very end, I would say that just doing 10% or 50% of real hardware synthesis, we are able to provide good acceleration. right? So efficient accelerators. So it's actually a good improvement, right? So I remember the very first design we had, doing 20 synthesis, 1 hour, it was like 20 hours to design that. So, well, we reduced that to 1, 2 hours. Still, we had the problem that we was mentioned this morning, right, of doing the compilation, the hardware synthesis more efficiently, but this is another problem that we have tackled so far. So that's the methodology. Let me tell you now how we have applied this methodology to frameworks, okay? Because we need to instantiate this methodology with frameworks. So the first one, obviously, we are targeting Edge, and the first framework we use is TensorFlow-like. You know, it's a framework for running the NN models on Edge devices. One important component of TF-Lite is the delegate system. The delegate system allows you to offload computation, right? So the bottlenecks of your computation to some backend. This backend can be so for hardware, right? And basically, initially, TF-Lite 1.0, they provided this NN API delegate for Android, Core ML delegate for iOS, but they didn't allow you to create your own delegates. Okay, without that, you are actually very limited, right? At some point in TF-Lite 2, they allowed you to create your own delegates, and we did that for our accelerators. So what happens, imagine that this is a neural network running, you have the data input, you, for example, execute on the CPU some quantization, then some padding. At some point, you have a set of layers together, convolution, quantization, ReLU, and you want to offload this thing to accelerator. Well, you can have several delegates, and I will show you later. You can have a delegate to offload this thing, do the computation, and come back, right? And hopefully you have done this properly. This is going to be much faster than running on the CPU. That's the idea. So Sept TF-Lite is a toolkit for designing custom FPGA-based accelerators, instantiating TF-Lite. So basically, so we published this expanded version on JPPC last year. And essentially, so as I mentioned before, you have a model here, eventually some convolutional layer, for example, you offload to a specific Sept delegate, and then, well, you have a driver here that manages so the communication, and as I mentioned before, you can do simulation or real hardware. It's worth mentioning that here, the devices we are using, they use the AXI interface, bus interface, because, you know, it's present in many of these devices, right? With mostly ARM cores and small FPGAs. So one important thing is that you can also use multi-threading. So the CPU can also have more than one core, and you can actually use these cores in order to pipeline, for example, the execution. And the time that you are sending some information, you can be preparing something new, right? Just to keep the pipeline busy. Okay, that's the idea. So as a case study, we demonstrated this Sept TF-Lite with 3 gen-based accelerators. Basically, we developed 2 for convolutional layers, vector MAC and systolic array, and also 1 for transformers for fully connected layers. So we call them vector MAC, systolic array, and FG, FC, yeah. So I'm not going to go into the details. You can go to the paper, but as you can see, well, some common things, we have a scheduler that basically is used to map, you know, pieces of the computation onto the processing elements of the accelerators, buffers, and so on, based on the architecture. So it follows a vector MAC, systolic array, or also here, so a MAC array design, okay? Again, the details are on the paper. So what is the runtime model? So what is happening when Sept TF-Lite is running? So essentially, TF-Lite has an interpreter that gets the model, and the model is passed to the corresponding delegate, wherever we need to offload some computation, otherwise it's run on the CPU. And this driver interacts with the main memory, right, of the device, and through the AXI interface is passing back and forth the information to the accelerator, okay, data and results. This is the execution model. Right, so this is the Edge device we use, is the pin Sept1 board. Now we are using the Sept2 model, but it's pretty much the same. Essentially, we have an ARM A9 dual core here, plus an Edge FPGA, very small, but still enough to do the job, right? So we proved this thing with 9 DNN models, 7 CNNs, and 2 BERT models for these 2 data sets. We were using ImageNet because sometimes you see executions from Edge devices and people are running Cypher10, right, which is a very small toy data set. So we use really ImageNet, which is the the standard for image classification, right? So basically what we did here is to compare the execution of our CPU plus accelerator versus the CPU 1 and 2 threads, right? At the moment that we did this paper, we didn't find any solution, right? Any specialized accelerator to directly compare with. We found one actually. So the VTA is the accelerator that the framework, TBM framework provides, right? So you have the compiler framework and they develop an accelerator. They only provided a couple of models, and we were able only to compare, if I remember, ResNet 18 and 50, and yeah, I think we were better 3x's. But overall, these are the results we got. Compared with 2 threads CPU, I insist that we also compared with the only existing accelerator at this point, and we got 3.5 and 2.5 speed up. for CNN and BERT models, and a big also savings in energy. So as you can see here clearly, the design works, okay? And the methodology and the instantiation works. Okay, so time continued, and well, as you know, LLMs have come to be here, and well, I'm not going to introduce LLMs, just to mention, has been mentioned several times today, that we have crazy big models, right? So one of the latest one, I put here 340 billion parameters, and I think we are already 700 billion, right? Something like that. So really crazy. So, well, something, I gave a similar talk two weeks ago, and someone told me, okay, are you going to run these models on this tiny device thing? Obviously, no, right? But, you know, there are different types, other versions of LLMs. Actually, I don't know if you have heard now, the term small language models has also come into play. So there are also models, right, that for particular applications make sense to run on edge devices. Obviously, GPT-3, no, right? It's huge, and obviously you are not going to be able to run it here. But for other types of application, yes, the answer is yes. So what we did is to consider one of the emerging frameworks for LLMs, Llama CPP, which is essentially a pure C++ library with minimal external dependencies that basically allows you to run stuff or run models in a wide variety of hardware devices, right? So they support, Llama CPP supports multimodal, custom, and also well-known models like, you know, Llama, Falcon, and GPT, and Gemma. And one of the key points, right, is that they use a wide variety of quantization running up to 1.5 bits. I think this morning, Christina, you mentioned also that you were using 1.58 bits. Right. So that's the trick, right? So that it's able to compress the models dramatically. Well, the problem is that when you compress that much, you lose a lot of accuracy, and you need to do some tricks to recover that accuracy, right? So, well, as you can see, this is the interest based on GitHub stars of Llama CPP, or this is another Whisper, another tool from the same team, how this number of stars has increased in the last months dramatically, right? So, well, this told us that Llama CPP is really the framework to use for this work. Right, so LLMs and SLMs on edge devices for several reasons. I'm not going to go very deep on that, but it makes sense to run them. For particular applications, it makes sense to run them on edge devices, okay? So then, Sept.LLM, as you can imagine, I just presented you Sept.TF-Lite. Sept.LLM is essentially the same, but we are now using Llama CPP instead of Sept.TF-Lite. So what you can see here is that our methodology can be instantiated relatively easy with other frameworks. Actually, we have some colleagues from a university in the US that they are actually creating Sept PyTorch, right? So they use PyTorch board and they want to instantiate our tool with PyTorch, which we are very happy to know that people are using this. So I presented myself, this is a very initial work, right? So I presented this work in ISCA last June in Argentina in a workshop. And, you know, basically, we have an initial development. We are working now on a full paper that hopefully we will submit to some architecture conference in a few months. But, you know, the idea is that, you know, we connect with Llama CPP. How do we do that? Well, essentially the same as we did before, right? So before we have the delegates, here what we have is a backend, GGML backend, and essentially we have a context holder that for every operation that we want to offload, matmul or convolution, whatever, right? So essentially creates a specific link, let's say, with the accelerator type, okay? But the interesting thing is that, you know, in both cases, you can use this driver both when you are doing real hardware execution or simulation, okay? So without going into the details, well, this is how it is connected, right? And well, these are the main components. So this is the input of the LLM, so graph executor that basically reorders the layers to grab them efficiently, and then this context handler, which is in charge of offloading the computation. Right. So the simulation design loop is the same as before, so I'm not going to go into the details because it's exactly the same, it's the same methodology, so nothing new here. And the hardware generation and evaluation is also the same. So as I mentioned before, the key idea here to iterate over the design is to combine a lot of simulation with hardware execution. And it's all about profiling. So one of the tools my students have been developing over the last months is to have a strong profiling tool to actually get more and more metrics and information to actually guide your design. Okay, that's the idea. So for this particular case, what we accelerated was matmul operation, you know, because for the model that we use as a proof of concept, Tiny Llama, actually 97% of the computation is matmul. So it's a good model to improve, right? So to accelerate. So what we did here, as I mentioned before, Llama CPP provides you a lot of quantization schemes, and we were using one particular, is called block floating point quantization. So particularly, we use the Q3K, Q8K configuration. So this actually provides 3 configured quantization, and this was just used for the weights, and for the inputs, we use another format, right, that provides 9.1 bit quantization. So the reason of using 3.5 is, as I said, initially we quantized to 3, but we lost like 10% of accuracy, and this is not acceptable, of course. If you are having a sensitive application, well, the user is going to say, no, I cannot afford to lose 10% of accuracy. So the idea is just to give you an example of how this thing works. So basically, imagine that we have a set of weights here, quantized to 3 bits. What we do is to group in blocks here. Right? For example, all these values correspond to this block. So every value of 3 bits here, I multiply by this scalar, block scalar, and then finally by this super block scale, right? And doing that at the end of the day, so from losing 10% of accuracy, we ended up losing less than 1%. So which gives you an acceptable rate for accepted by the user. So this is it. So then this is the design that we use for this particular accelerator. And well, the idea here that also brings on the table the hardware-software co-design is that so the vector processor actually is tuned or tailored to this type of specific quantization. And the thing is that if you have another type of quantization, you can also tune the vector processing units for that. Okay. So essentially, this vector processor exploits the parallelism across supergroups. Okay. So if you want to know more details, as I said, we can chat offline or we can have a look at the paper. So same as before, the runtime model is exactly the same as IRTF, right? The only difference is that we are, having this the accelerator driver, the component I mentioned before, and also the backend is also different and tailored to Llama CDP. Otherwise, the rest is the same, right? And if we bring to model some other framework, it's going to be the same execution model. Let me give you some numbers. Again, we use the same board. In this case, we use this tiny Llama, which is a 1.1 billion parameters model, right? So translated into megabytes, almost 500 megabytes. Right? So we use this quantization, as I mentioned before, the Guanaco dataset, and we compare. In this case, unfortunately, we didn't find anything that we think we could compare against fairly, right? And for now, we are, I'm just providing you the initial evaluation. Of course, for the extended paper, we want to find some competitors and hopefully show that we are better. So these are the results. So we obtained, compared with the two-thread execution, an 11x speed up. Essentially, we moved from, running every token in 19 seconds or every word in 26 seconds to 1.5 seconds per token. Someone can tell me, well, this is still is very slow. True, you're right? But this is a very small device, right? So look at how powerful is the A9 core and also the small FPGA that we have. This is a big first step towards having, more efficient execution. So something you can see here is that using two threads, well, we don't get much improvement. So actually, we have zero improvement, and the reason is because this problem is memory bound, not compute bound. In this graph, I just want to show you how actually for this design we did 3 iterations, and this is how the execution time changed over iterating the design, right? So we went from here to here, right? So version 1, 2, and 3. Clear, more or less? Right. So let me show you the last work we did. So, okay, I have shown you how to, define an accelerator and so on. But at some point, we realized that, once you have an accelerator, generate efficient code, efficient driver code that can actually exploit to the best this hardware is not easy and takes time. It's very time consuming, right? And actually, I can tell you that this is what happened with us also. So the solution we found for that is, can we generate this code automatically? And well, we published this work this year at CTO. And essentially, this is what we did. The work is done actually for MLIR. And essentially, basically what we do is to base the features of the specialized accelerator, we pass some of this information to MLIR, to a specific dialect of MLIR, and we generate the code automatically, just in one click. Okay? And I will show you that in addition to that, we get performance improvement, which was not the initial goal that we had. But obviously, at the end of the day, we want to get more performance. So what is our vision? I think we were discussing also in the lunch break about that. Our vision is to, at some point, have a high level or domain scientist, application scientists that can generate accelerators automatically, transparently, without having knowledge about hardware. Okay, so the MLIR automation this is actually a first step towards that. Okay, and we are also currently improving and expanding this work. So just to give you a rough idea of what actually for MLIR is, well, MLIR is a unifying software framework for compiler development. It's a sub-project of LLVM. And essentially what we did is to extend MLIR, right? So the dialect with, particular information of the accelerator. So what we do is to pass some opcodes that or features that the accelerator is able to execute, and the code generator is going to tune the code, the kernels, based on these parameters, right? And just doing a simple allocation of these parameters, we were impressed to get a very big improvement, and not only that, generate the code in one click. Okay. So I think it's a good first step. So, well, I'm not going to go into many details, but essentially what we do, we provide this acceleration information, also the host CPU information. The compiler parses this information and actually takes into account every time a kernel comes. So the kernel comes, I have this information, I can say, okay, for this problem size, for this accelerator size, that's the best instantiation of the kernel, and I'm going to map it in that way. Okay. So this is the design. So actually, we designed a family of accelerators, of mul accelerators, based on different parameters, the tile sizes, the opcodes, and the data flow. Here, the idea is that we use different data flows, input data flow, input stationary, output stationary, no data flow at all, and and different sizes. This is what we did. So, well, this is the accelerator itself is based on a MAC array, and there are a bunch of buffers actually to put the input matrices, and well, obviously this accelerator is for matrix multiplication only, not full models. But essentially, and this is the main result, so here I'm showing you a bunch of instantiations of these accelerators based on the dimensions of the input, the accelerator size, the data flow version, and in the end, we got 1.65% of improvement, okay? Also, reducing the CATS reference up to 56% of the original. So I think this is a great improvement, a great first step, assuming that we did it relatively quickly, right? So, well, you can say, what about full models? We also run full models, right? And we also instantiated convolution layers rather than MATMULs. And here are some results. I'm not going to discuss them. You can go to the paper. And that's all, more or less. Let me just to recap. So SECDA is a design methodology to efficiently reduce the development of FPGA-based accelerator, specialized FPGA accelerator. Sept TF-Lite is a new open source toolkit. Please have a look at the website and use it yourself, right, to develop accelerators based on TF-Lite. SECDA LLM is another toolkit, not still open source, but we are working on it to also give it to the community to do the same for LLMs. And instantiated the Llama CPP. And next for MLIR extends the MLIR compiler in order to generate code automatically and with better performance. So some lines of future work that we're going to focus on is, support more layers, for example, host convolution, more cores. We are working on shift-based accelerators. Instead of doing, multiplication, we can do shifting, right? Also, as I mentioned before, some colleagues in US, they are instantiating the SECDA PyTorch tool. And, SECDA LLM is not open yet, but we plan to do it. And, here is a bunch of projects that we are planning to do, create a SECDA MLIR, right? So an MLIR dialog that generates directly system C accelerators. We have been also working with colleagues at ETH Zurich in order to do SECDA-P. We're going to integrate processing memory. And, also more tools to improve the whole process. And, other potential future things like focusing on genome analysis or training. So finally, I want to thank my students, my collaborators, and the people that give us the money. So thank you to all of them, and I'm happy to answer any questions.
So, do we have questions?
Please, yes.
I have a question.
Yes.
This is at the beginning, maybe I missed something, but you were discussing about the design with HLS base and so forth. And my experience with HLS, it's great when things work. When things don't work, I don't know how to deal with them. So how do you introduce the human in the loop in your tools, or if there is a thought about that?
Well, at the point when we generate the HLS process starts, we don't do much. Well, I have to say, to be frank, right, that we have had some problems with the pragmas. Sometimes the pragmas generated are not the ones you want, and actually you can get even compilation errors. That's true, but I would say that so far we haven't had many problems on that. Even though that sometimes, we actually don't get what we were expecting to get. This is true, that happens. But overall, as I showed, right, so the results are satisfactory, I would say, right? Another question? Please.
You've shown how Sector works on the edge. Is there any reason why it can't work for data center applications?
For a second, I couldn't hear.
Are there any reasons why it can't work for data center applications?
data center?
Oh, data center. Oh, right. Okay, yes. Because I mean, I think that for more powerful FPGAs, for more powerful device, I think there are more tools. So the challenge that we found here is that for particularly edge development, we didn't find much tools available, to be honest, right? Well, we found Pin, for example, that was mentioned today, but Pin is more a compiler, as Michaela mentioned. It's not actually a framework for developing accelerators. And, you know, our solution is more general, right? Yeah, I don't know, because as I mentioned, I do believe that the edge is also has a lot of things still to do, right? So, well, we need to have people in both sides, right? So.
Please.
Thanks for the talk. I have a question about your matrix multiple accelerator.
Yes.
So it's like, did you design a matrix with certain sizes depending on the specific architecture, or your accelerator can compute like matrix with different sizes for the same architecture?
Yeah, it can. So basically, so the thing is that at the end, so based on the fabric of the FPGA, you can accommodate a given size of accelerator, right? So as I mentioned, as I showed you before, we have played with different sizes, but you know, if the matrix that you have is larger, basically you need to do something, right? You need to do tiling or apply some optimizations in order to split that computation and you know keep sending chunks of it if it doesn't fit, obviously. Yeah.
Have another question? In that case, can I ask a naive question?
Sure.
You talked about the hierarchical blocked floating point number representation.
Yeah.
And you talked about how using a less elaborate precision reduction led to a substantial loss in accuracy. Did you retrain the model when you did that?
No.